if we are passing a signal through a linear time invariant system and we are getting an output yt, and this transmission, this is called a distortionless transmission if the output signal satisfies two conditions. Okay, if the output signal, the definition is if the output signal is, if yt is an exact replica of xt. When we say that it is an exact replica, we can say that it is of this form. That means the transmission that preserves the shape of the signal, and when we say that it is a constant times xt minus t naught. So what are the operations involved here? So can we say that the output signal is same as the input signal except for two things? What are those two things? One, there is a scaling factor. Okay, its amplitude is changed. Amplitude is changed by a constant factor c. And then what about this? T naught. That means it is a delayed version of the input signal. Then we can say that it is a distortionless transmission. For example, let's say you are transmitting a signal like this. When can we say that it is a distortionless transmission? If the output is delayed by some time, let's say this is 1 and this is 3 and this is 1 and this is, let's say, 5. Okay, so we can say that it is a distortionless transmission if the only operations that affect the signals are signal is only the amplitude change and a delay operation. So that is the only two the distortion caused by that system. Then we can say that it is a distortionless system. Okay, so please remember that these are the only two operations allowed. If you are considering x to t, xt to x2t, this is not a distortionless transmission. Even though maybe we can say that the shape is preserved. If you pass a rectangular triangular pulse, the output is also a triangular pulse, but that is not a distortionless transmission. In distortionless transmission, only there is a delay and an amplitude scaling. Okay. Now, can you tell me what if we consider a distortionless system, what will be the frequency response of such system? If we are giving xt as the input, output is a constant times xt minus t naught. This is yt. Okay. If we take the Fourier transform on both sides, we'll get x of j omega here, and this is constant times x of j omega into e to the power minus j omega t naught. What is the frequency response of this system? This is y of j omega. How do we define the frequency response of this system? H of j omega is y of j omega divided by x of j omega. So it is c into e to the power minus j omega t naught. Is it the frequency response of this system? This is the frequency response of a distortionless system. Now, can you tell me what is the magnitude response of that system, of a distortionless system? If we plot the magnitude response, what is the shape of that?
So it will be constant C.
It will be a constant C, isn't it? Because this is the frequency response. If we take the magnitude of that, it is constant C. And what about the phase response? What will be the phase response of the system?
So it will be a y equals to minus x type line, negative line, passing through origin.
Is it this?
Yes, sir.
Because okay, it is a this with slope. What is the slope of this? Minus t naught, isn't it? This is called a linear phase system. linear phase. Okay, this is the frequency response of a distortionless system. Now, can you tell me what is the significance of these two? Amplitude must be a constant and the phase must be linear for a distortionless system. What are we doing in Fourier transform and Fourier series representation? Are we expressing a signal in terms of complex exponential signals? In the case of Fourier series, it is a linear combination, and linear combination in the form of summation of harmonically related complex exponential. And in the case of Fourier transform, it is an integration. Still, we can consider it as a linear combination. So now when we say that if xt is the input signal and the output signal is scaled by a factor of c and delayed by t naught, what will happen to these complex exponentials or the sinusoidal signals? We are expressing a signal as a linear combination of sinusoidal signals. That is what we are doing in Fourier representation. So if we delay the signal and multiply it by the constant, what will happen to that sinusoids to preserve the shape? Can we say that all the sinusoids should be multiplied by the same constant c? Is it required? That is this. All the sinusoids are multiplied by the same constant factor c. And what about this? What is the significance of this? We are delaying each sinusoid by the same amount t naught. That's why we are getting a phase like this. Okay, then we will get a constant times c times the input signal delayed by t naught. If we delay all the signals by the same amount t naught. Okay, now we can define what is called a filter. Can you tell me what is how can we define a filter? What is a filter? Can we say that it is a frequency selective device? Frequency selective means it passes certain frequency bands and eliminates other frequencies. Is it the filter that you have studied?
Yes, sir.
So we can say that it is a frequency selective device. It passes certain frequency bands and removes other frequency bands. Okay, so when we say that it passes certain frequency bands and removes other frequencies, we can define two bands. One is called a pass band. Okay, and the other one is called a stop band. Okay, what is pass band? We can define the pass band of a filter as a range of frequencies which are passed by the system. That is called the pass band. And stop band means the range of the frequency range which are eliminated by the filter. That is called the stop band of a filter. Okay, and more precisely, we can say that it passes frequencies in the passband. Instead of that, we can say that it allows distortionless transmission in the passband and it eliminates the frequencies in the stop band. Now, as you said, you have studied different types of filters. Let us start with the filter, low pass filter. Okay, can you tell me what is the frequency response of a low pass filter? Frequency response means, okay, we have to sketch h of j omega and phase of that. Okay, can you tell me what is the shape of that phase response? Magnitude response and phase response. First, let us start with the magnitude response. It passes certain band of frequencies. Okay, this is zero frequency, and if we are increasing this, I am saying that up to a frequency omega c, it passes and it eliminates other frequencies. So can we say that this is the magnitude response? Is it the magnitude response of a low pass filter? What is the meaning of low pass filter? It passes low frequencies and removes high frequencies. So this is up to this. And since we are considering distortionless transmission, okay, let's say it is C. Now what will happen in the negative side for the negative frequencies? For the negative frequencies, what will happen?
Image about y-axis.
And why is it an image about y-axis? It can be something else also. The reason why we generally consider the image about y-axis. The reason, can you tell me the reason?
Sir, because like magnitude wise, if we see till there, it will be same.
Till there it will be the same. And the reason is that all the practical filters, the impulse response is real valued, isn't it? Yeah, if HT is real valued, then what should be its frequency response? That is the conjugate symmetry property we have already discussed. If xt is a signal which is having xt is a real valued signal, then its frequency it's for a spectrum. What is the relation with the spectrum? X of j omega is equal to x star minus j omega. That is the conjugate symmetry property. This implies that its magnitude spectrum must be an even function of omega and phase spectrum must be an odd function of omega. That is why we generally take like this, minus omega c to omega ct. These are, in fact, these are same frequencies only. What is the difference between these frequencies? Positive and negative frequencies? What is the meaning of negative frequency?
Direction of rotation.
In the opposite
Yeah,
direction.
in terms, because if you consider a particular frequency, let's say omega naught, we can consider it as a phasor rotating in the clockwise direction. And when you consider minus omega naught t, it is a phasor rotating in the clockwise direction. Okay. Okay. Omega naught is in the anti-clockwise direction and minus omega naught in the clockwise direction. So that is the only difference. So this is the magnitude response of a low pass filter. I would say an ideal low pass filter. Low pass filter. Magnitude response of an ideal low pass filter. Now, can you tell me what is the frequency phase response of an ideal low pass filter? How do we define a filter? It allows distortionless transmission in the pass band and eliminates the frequencies in the stop band. So can you tell me first, tell me which is the pass band of this filter and which is the stop band of this filter? Is this the pass band minus omega c to omega c? The filter passes frequencies in that range. This is the pass band omega c to minus omega c to omega c. That is the pass band of this low pass filter. And what is the stop band?
So frequencies above omega c.
Frequencies of above omega c and below minus omega c, isn't it? This is pass band. This is stop band, isn't it? Above omega c and below minus omega c. That is the stop band. Now tell me, what is the phase response of this low pass filter? It should be a distortionless transmission in the pass band. So what should be the shape of that phase response in that pass band? Minus omega c to omega c. Is it something like this? Distortionless transmission we have just discussed now. Now we discussed the magnitude response should be a constant and phase response should be a linear function of omega. Okay. So this is the magnitude response and this is the phase response of an ideal low pass filter. And generally we don't sketch it beyond this omega c. The reason is that anyway that the magnitude is zero. Those frequencies are eliminated. So this is not important. Whatever be the phase response, those frequencies are removed. And in some textbooks, it is given like this also. It is 0 outside that. But that doesn't matter. Outside this band, what is happening, that is not important. Okay. So that is a low pass filter that removes that passes low frequencies and removes high frequencies. Okay. What is a high pass filter? High pass filter. Can we say that high pass filter is a filter that passes high frequencies and removes low frequencies? So what is the magnitude response of a high pass filter? Is it something like this? Omega C minus omega C. That means it passes frequencies above omega C and below minus omega C. And these are low frequencies. These frequencies are removed by the system. Okay, or eliminated by the system. It passes frequencies above omega C, and its counterpart in the negative frequency range is below minus omega C. So it passes frequencies in this range, but eliminates frequencies from this frequency band. It eliminates those frequencies. Okay. So this is the pass band. This is pass band. And this frequency range minus omega C to omega C, this is called the stop band of the filter. Okay. And this omega C, that is called the cutoff frequency. Cutoff frequency of the filter. What about the phase response of the system? It is distortionless transmission in this frequency, in the pass band, isn't it? So it must be a linear function in this pass band. Okay. And okay, there is generally it is like this only. Okay, it is a linear function in the pass band. Now, have you heard about other type of filters? Some other type of filters other than low pass filter and high pass filter?
So the band pass filter.
Band pass filter. What is a band pass filter? What is band pass? Can we say that it passes a band of frequencies?
Yes, sir. Some specific range of.
Some specific range of frequencies. This is the magnitude response of a band pass filter. It passes a band of frequencies and eliminates other frequencies. I am denoting it by omega C1 and omega C2. It is minus omega C1 minus omega C2. These are the cutoff frequencies. So here the pass band is between these frequencies are the pass band frequencies, and these frequencies, those are the stop band frequencies. Okay, have you heard about any other type of filters other than this? Other than these three type of filters? Low pass, high pass, and band pass. There is band stop filter. Can you tell me what is a band stop filter? From that name, band stop.
The inverse.
Yeah, it is not inverse. It is we can say that it stops frequencies in a certain band. And passes other frequencies unattenuated. Okay, it eliminates frequencies in a narrow band of frequencies and it passes other frequencies. This is called a band stop filter. And one application of this band stop filter is in many electrical this measurement systems. For example, if you are using an AC of 50 hertz frequency, isn't it? The power supply. And in many applications like ECG and EEG, this is particularly used in ECG and EEG applications. This this power supply, this will interfere with the ECG and EEG signals. So what we do is we know the exact frequency of the interfering signal. So it is passed through a band pass filter, a band stop filter that eliminates exactly that frequency. Okay. So that is one application of band stop filter. So if we in this particular application, we can design a band stop filter which eliminates exactly the 50 kilohertz frequency. Okay. Any other type of filters? So we have discussed low pass filter, band pass filter, low pass, high pass filter, band pass filter, then band stop filter. Any other type of filter? There is something called all pass filter. Okay. Why that all pass filter? If it passes everything, but then why is it called a filter? First of all, tell me what is the magnitude response of an all pass filter? Should it be something like this? It is constant for all the frequencies.
Yes, sir.
And phase response? Is it something like this?
Yes, sir.
So all pass filter means it introduces some phase shift. That is only purpose. Okay. Or time delay. Output is a delayed version. This is a particular class of filters known as frequency selective filter. Frequency selective filters. That means it selects, it passes only a certain band of frequencies. Okay, that is called a frequency selective filter. And there is another category of filters that is known as frequency shaping filters. Okay, frequency shaping filter means if you have a filter, let's say h of j omega and x of j omega, y of j omega is the output spectrum. Frequency shaping filter means it changes the shape of the spectrum of the input signal. It won't remove any frequencies, but it changes the shape of the spectrum. That is called frequency shaping filters. And you have seen, I'm sure that all of you have used this frequency shaping filters. It is used in audio equalizers. Have you used an equalizer? There is a sliding bar, you can adjust the frequencies. Have you used that in an audio system?
Yes, sir.
Audio equalizer. So it is, there are a number of channels. When we talk about equalizer, we talk about 5-channel equalizer. What do you mean by 5-channel equalizer? Or can you tell me, if you slide the bar, you can slide that bar, isn't it? Equalizer bar. What is happening when you're sliding the bar? Can we say that, okay, let's say 20 hertz to 20 kilohertz. We are in a five channel. I'll take the example of a 5-channel this equalizer. It is divided into 5 frequency bands, and this is not generally done in the linear scale. It is normally done in the octave scale. Okay, have you heard that term, octave? Okay, forget about that. We are dividing it into let's say 1, 2, 3, 4, and 5 bands. Okay. Now what an equalizer do is you can amplify or attenuate signals in that particular frequency band, or you can increase the gain or reduce the gain of in that particular frequency band. That is, for example, if you have a, okay, let's say 5-band equalizer. Okay, this is a graphic equalizer, and there is a sliding bar. If you increase the, for example, if you are increasing this, if you are moving this sliding bar up, what is happening is you are increasing the gain in this particular frequency band. Okay, so can we now explain this in terms of a this band pass filters? Can we say that it consists of 5 band pass filters? There are, I'm assuming that there are 5 channels. Okay, it is passed through, and there is it will be combined. All these will be combined. Okay, so this is 1, 2, 3. Is this an equalizer? There are 5 different band pass filters. Now, if you are, let's say you are increasing the value of that second channel, what we do is we are increasing the gain of the second band pass filter. Is it summation here?
Yes, sir, the superposition only.
Yeah, we have to combine all these signals, and when you slide that's when you are sliding that bar of a particular channel, what we are doing is we are increasing the gain of this filter, the magnitude response. It is a constant for that particular frequency band, corresponding frequency band. We are increasing that, and correspondingly we can similarly we can adjust the relative frequency. For example, if we want to enhance the bass, that means you have to enhance the low frequencies. You have to increase the gain corresponding to this band pass filter. Okay, then you will increase the bass. And if you want to increase the high frequencies, that treble, then you have to increase the gain corresponding to this band pass filter. Okay, so that is what you do when you slide that graphic equalizer bar. Okay.
So, sir, this is not distortionless transmission?
This is not distortionless transmission. You're right. This is not distortionless transmission, because you can see that if you change the spectrum in a particular band, it is not a distortionless transmission. It is not a replica of the input signal. You are changing something, isn't it?
Yes, sir.
It is not distortionless transmission.
Okay, sir.
Filter. So when we talk about this low pass filter, band pass filter, a high pass filter, band stop filter, and all pass filter, I have mentioned that these are all called ideal filters. What I have explained is ideal filters. Okay, that means let us take the example of a ideal low pass filter. This is the magnitude response of an ideal low pass filter, but this is not a physically realizable filter. Can you tell me the reason for that? This is not a physically realizable filter. What type of filter is that? It is a low pass filter. Can you tell me what is its impulse response? If it is a rectangular pulse in the frequency domain, what is its shape in the time domain? This is h of j omega. I am talking about ht. What is the inverse Fourier transform of this?
Sir, a sinc function.
It is a sinc function, isn't it? It is a sinc function. Okay. This is not a physically realizable signal. There are two reasons. One is it is anyway for a real-time filter. This is a non-causal filter. Is it non-causal system? Is it a non-causal system? ST is non-zero from minus infinity to infinity. It is a non-causal system. So you will study about the details of filter design in some other course. later on you will see that it is not possible to make a magnitude spectrum like this exactly constant. You cannot make exactly 0 in the stop band and exactly a constant in the pass band. It is not physically realizable. So what we do in practical applications is, for example, if you consider a low pass filter, instead of making it a constant, we design a filter such that its magnitude response is within this range. It is not a constant. It can be within this range in the pass band, and in the stop band also it is not exactly 0. We can allow a small variation in that. So generally it is like this. And the stop band also, there is something called a transition band. Okay. So the cutoff here, the cutoff frequency, there is a steep transition from the pass band to the stop band. In practical filters, there is a gradual transition. Okay. And normally it is something like this. There are some ripples in the pass band and stop band. And later on, you will study mainly two types of filter design. One is called, I don't know, you have heard it already or not, Butterworth filter. Have you heard this term, Butterworth, in your circuit theory course? Have you heard this term, Butterworth filter?
No ideas. I don't know if we have it, sir.
Okay. Okay, so that we'll see later on. Okay, and okay, so what I want to say is, in the passband it is not exactly constant. We allow small deviation from that constant that condition, and in the stop band also it is not exactly 0. It is in a very small range. We can vary it. It will vary in a small range of frequencies. Okay, now just one more thing. This is all about continuous time filters. Now, what about a discrete time filter? I will just explain the shape of the magnitude response and phase response. Let us start with a low pass filter. Okay, and in the case of a discrete time system, it is h e to the power j omega. If you consider the Fourier transform of a discrete time signal, and if it is x of e to the power j omega, this is 2 pi periodic. Is it? Now, can you tell me, if it is 2 pi periodic, means which are the high frequencies and which are the low frequencies? So we have to plot from minus pi to pi, because since it is 2 pi periodic, we can plot it in a continuous interval 0. Let's say I'm denoting it by 0 to 2 pi. Okay. Can you tell me which is the high frequency? Is it 2 pi, highest frequency for a discrete time signal? Is it 2 pi, high frequency, or pi? So when we talk about a discrete time signal, the frequencies near pi, these are called the high frequencies. And frequencies near 0, these are low frequencies. And since it is 2 pi periodic, we generally sketch the magnitude response from minus pi to any interval 2 pi. And let's say I am considering the interval from minus pi to pi. Now, can you tell me what will be the frequency response, magnitude response of a discrete time low pass filter? This is the low frequencies. So the system must pass low frequencies and removes high frequencies. Is it something like this? And since it is 2 pi periodic, that pattern repeats. This is minus pi. This is again minus 2 pi. It is a periodic pattern. Is it that? Magnitude response of a low pass filter. Now, what about a high pass filter? Frequencies, if you consider frequencies from 0 to pi, this is increasing direction of frequencies. If we can increase this, and frequencies near pi are called the high frequencies. So high pass filter means it passes frequencies near pi. So here also it is frequencies near pi. Okay. Is it 2 pi periodic? Because it is discrete time signal. So will we get something like this? Because this portion comes from here, and this portion comes from here, shifting by 2 pi. So this is the frequency response of a discrete time high pass filter. Okay. It is 2 pi periodic. Similarly, you can find the frequency response of band pass and band stop filters. Any question regarding this frequency response of discrete time filters?
Sir, I have a question. Sir, in the low pass filter for discrete type, we are having like the signal for frequency.
Sorry, frequency?
Pi.
Okay, let's consider a low pass filter. Low pass filter. Okay, anyway, first of all, it is 2 pi periodic, so we need to sketch it only for interval 2 pi. Then it is a periodic repetition. Okay, so when you consider this frequency interval, these are the low frequencies, and the frequencies near pi are the high frequencies. So it passes only low frequencies and eliminates high frequencies. And in the negative side, since we are assuming a real valued filter, it must satisfy this symmetry. Okay. So this is the magnitude spectrum of an ideal low pass filter in this range. Now we know that this is 2 pi periodic. So this is 2 pi minus 2 pi. It is just a periodic extension. Is it something like this? This part, it repeats. Does it answer your question?
Yes, sir, somewhat. I'll think about it.
Okay. So you may be confused with this yeah, high pass filter. High pass filter means if you consider this frequency band, I'll explain once again how to find the magnitude response. This is pi minus pi. So frequencies near this, these are high frequencies. Okay, it passes these high frequencies. Okay, I am drawing like this pi. Now, if we consider a periodic extension, this part will come where? Will it come here? This plus 2 pi is this.
Yes, sir.
And this part will come in the negative side, it will be here. So its magnitude response is something like this. Then this pattern will repeat 2 pi periodic. That is, this is coming here, then this will repeat at 3 pi, isn't it? And this is 2 pi, it is this one, it is 0. It is 2 pi periodic. You can easily find that. Okay.
Yes, sir.